Process is defined as an entity which represents the basic unit of the work to be implemented in the system. The execution of a process must progress in a sequential fashion. As shown in the diagram, the components of a process are stacks, heap, text, and data. Stacks are fundamental to function calls. Each time a function is called, it gets a new stack frame. This is an area of memory which usually contains the address to return to when complete, the input arguments to the function, and space for local variables. Statically allocated memory is stored in the form of stacks. The heap is memory set aside for dynamic allocation. Unlike the stack, there is no enforced pattern to the allocation and deallocation of blocks from the heap. You can allocate a block at any time and free it at any time. This makes it much more complex to keep track of which parts of the heap are allocated or free at any given time. Text includes the current activity represented by the value of program counter and the contents of the processor's registers. The data section contains the global and static variables. Process control block. The PCB or the process control block is a data structure in operating system kernel containing the information needed to manage a particular process. It is the manifestation of a process in an operating system. Each process is represented in the OS by a process control block or task control block. The role of the PCBs is central in process management. They are accessed or modified by most OS utilities, including those involved with scheduling, memory, and input-output resource access and performance monitoring. The set of the PCBs defines the current state of the operating system. Data structuring for processes is often done in terms of PCBs. The process control block contains process control information. The components are described in the diagram shown. Process state. This describes the current state of the process, that is, whether it is waiting, ready, or running. Program counter. The counter indicates the address of the next instruction to be executed for this process. CPU registers. A process is stored for execution in the running state in these registers. These registers vary in number and type depending on the computer architecture. They include accumulators, index registers, stack pointers, and general purpose registers, plus any condition code information. Along with the program counter, this state information must be saved when an interrupt occurs to allow the process to be continued correctly afterward. CPU scheduling information indicates the information of a process with which it uses the CPU time through scheduling. This information includes a process priority, pointers to scheduling queues, and any other scheduling parameters. Memory management information. This information may include such information as the value of the base and limit registers, the page tables, or the segment tables, depending on the memory system used by the operating system. Accounting information. This information includes the amount of CPU and real time used, time limits, account numbers, job or process numbers, and so on. Input-output status information. This information includes the list of input-output devices allocated to the process, a list of open files, and so on. Since PCB contains the critical information for the process, it must be kept in an area of memory protected from normal user access. In some operating systems, the PCB is placed in the beginning of a kernel stack of the process since that is a convenient protected location. Process states. The process state determines whether the given process has executed or whether it is waiting for some input or output from the user, or if the process is waiting for the CPU to run the program after the completion of the process. There are 5 elementary states in which a process can exist. New state. When a user requests a service from the system, then the system will first initialize the process. So every new operation which is requested to the system is said to be in the new state. Running state. When the program is being executed by the CPU, then this is called as the running process, and when a process is running, it will always provide some output. Waiting. When a process is in waiting state for some input and output operations, then this is in the waiting state. Ready state. When the process is ready to execute but is waiting for the CPU to execute, then it is in the ready state. After the completion of the input or output operation, the process will be in ready state, which means the process will wait for the processor to execute. Terminated state. After the completion of the process will be automatically terminated by the CPU. Two-state process model. This model is based on the fact that a process is either being executed by a processor or it is not. Thus, a process may be considered to be in one of two states, running or not running. While the OS creates a new process, the process is initially labeled as not running and is placed into a queue in the system in the not running state. The process then exists in main memory and it waits in a queue for an opportunity to be executed. After some period of time, the currently running process will be interrupted and moved from the running state to the not running state, making the process available for a different process. The dispatcher will then select one of the not running process from the queue to transfer to the processor. The chosen process will then relabel from a not running state to a running state, and its execution is either begun if it is a new process or is resumed if it is a process which was interrupted at an earlier stage. 5-state running model. The 2-state model to some extent reflects the behaviors of processes. However, the real situation is much more complex. We cannot simply deal with all the processes that are not running in the same way. For example, in a time-sharing system, a process may lose control of the processor just because of timeout, that is, its time slot is used up. Although it moves to the not running state, it is always ready to run right away. But some processes stop running to wait for the completion of input-output operation. Before the interrupt signal notifies the completion, it cannot run and make any progress and have to wait. Thus, it is not proper to use a single state and a single queue for all the not running processes. Naturally, the not running state is to be split into 2 states, ready and blocked. Thus, if the creation period and termination period of a process are also considered states, we will obtain a 5-state model as depicted in the diagram. The new state indicates a process has just been created but has not been admitted to the pool of executable processes by the operating system. Typically, a new process has not yet been loaded into main memory. For example, the operating system may limit the number of processes that may be in the system for reasons of performance or main memory limitation. The exit state indicates that a process has been released from the pool of executable processes by the operating system, either because it has halted or because it aborted for some reason. This state enables some accounting programs to record the processor time and other resources utilized by the process for billing purposes, or utility programs to extract the information about the history of the process for purposes related to performance or utilization analysis. Processes in the block state cannot execute until some event occurs, such as the completion of input-output operation, while a ready process is always prepared to execute when given the opportunity.